Hello everyone, this is lecture section 2.2. We're going to continue with our discussion of reduced echelon form by simplifying these augmented matrices a little bit more. So that was RREF here, lecture 21. So today we'll do a slightly refined version of this called the reduced row echelon form. And we'll introduce the notion of a rank, which is an important property of these matrices. So recall that in the last lecture 21, when we produced the row echelon form, and this process of row operations is called Gauss-Jordan elimination, we created leading ones in the system of equations or in the augmented matrix, the leading one. So in the system of equations, we created leading variables. We identified leading variables. Now what we're going to do to get to the reduced row echelon form is we're going to eliminate leading variables in all other equations than where the leading one is in the augmented matrix. Okay, so after we do that, the system of equations will contain a leading variable in exactly one equation. Okay, so no equation will contain more than one leading variable. All the other variables that appear in the equation, that is variables with non-zero coefficients, they will be free variables, and therefore we can use those equations to express the leading variable in terms of the free variables, and that's our final expression for our solution set. So let's look at one example here. I see the leading ones right here. So x1 is a leading one, x3 is a leading one, x4 is a leading one, and x2 is a free variable. So this is a row echelon form. I'm going to reduce it further, and I'm going to eliminate variables, leading variables in all the other equations which they occur that doesn't contain the leading one. So here's my column 1. Okay, so x1 occurs just in equation 1, and there's my second column, which is the free variable x2. Now I have my third column with the leading 1, and I'm going to use that column, row now, row 2, to eliminate the variables, non-zero variables above the leading 1. And I see there's a 3 there in my in my first row in the third column. So I'm going to do a row operation, and as I mentioned last lecture, the most commonly used row operation, the one that's the most useful, is this one that's actually the more involved row operation, where you're adding a multiple of one row to another. Okay, so here I'm going to multiply in my mind's eye row 2 by 3, and then I'm going to subtract it from the first row. Okay, so let's just do that in our heads. So when I get to that entry 3 in the top row, I see below it it's going to be a 3, and I'll get a 0. And then when I look at the 4, below it will be, in my mind's eye, a minus 3. So when I minus 1. When I subtract that, I'll get a 5. And then this 1 I see in the last entry in the first row, I will subtract from it a minus 3, which will give me a 4. Okay, so that would be the result of that row operation. Okay, so I would get that matrix now. Now let's continue further. So let's write down what we have so far. Okay, so I'm now working on the next leading variable, which is this one in row 3, x4. Okay, so I'm going to eliminate, I'm going to do this all at once. I'm going to eliminate the 2 non-zero entries above that leading one. That's these 2 terms. Okay, so I'm going to eliminate the leading variable x4 in my second and first equation. Okay, so focusing on the first equation at the top there, in my mind's eye, I'll multiply the third row by 5 and subtract it, so that will eliminate the 5, and the 4 will stay the same because there's a 0 in that column. And now for the second row, I'm going to multiply in my mind's eye the third row by a half and add it, so I'll get a 0, and that won't change the minus 1. Okay, so here we are. This is the reduced row echelon form, because above my leading ones are all zeros. So now my system of equations, if I wrote it out, would be quite simple. Let's write it out here just to illustrate one more time. I'd have x1 plus 2x2 equals 4. That's the first equation. And I'd have x3 equals minus 1. And I'd have x4 equals 0. So that's my system right now. Okay, so I can see that x2 is a free variable. So I'm going to set my free variable there. Free variable is x2. Okay, so I set x2 to be t. And now I express my solution set in terms of these free variables, in terms of the parameters. There's only one. So x1 becomes 4 minus 2t. X2 I specified to be t. X3 is minus 1. And x4 is 0. Okay. So let's do a check. Like I mentioned, it's always worth to check these things once in a while. So I'm going to take, in other words, my solution set, there's infinitely many because I can choose t freely. So I'll just choose one particular t to be minus 2, and then I'll calculate what corresponds to that solution. So x1 would be 4 plus 4, so it's 8. My x2 would be 2. My x3 is minus 1. My x4 is 0. Now, when I say check, try checking it with the original equation. So the original system of equations, let me just write it out here, would be x1 plus 2x2 plus 3x3 plus 4x4 equals 1. So that's the first equation. So let's check this solution here. Does it work? So let's just plug it in for x1, x2, x3, x4. So I get minus 2. I get 8, right, starting with 8, plus 4 is 12, and then minus, is that right? So x1 is 8 plus 4, okay, 2, oh, sorry, that's a minus 2, that's why, it doesn't make sense. There's my minus 2. So once again, so 8 for x1 minus 4 gives me 4, and then minus 3 plus 4. Okay, so minus 8 to minus 1. What did I say for x3 is minus 1? This is why it's not working. Sorry. See, little mistakes like that, you'll pick them up when you do this check. So one more time. So x1 is 8. x2 is minus 4. That gives me a 4. And then I'm going to subtract 3. I'll get a 1. And that's a solution for the first equation. Fine. So let's go to the second equation. It looks like it's x3. x3 minus 1/3 x4 minus 1/3 x4 equals minus 1. Okay, so let's see if that works. So I get minus 1. Sorry, for x3, I'll get minus 1, and x4 is 0. So that works for that one. And then my last equation is simply x4 equals 0, which I see is true. Okay, so I've selected from my infinite solution set, which is this one here, I've selected one solution to test. Okay, and I noticed I missed a few minus signs because of that, so I picked them up later. Okay, so let's go on and discuss this consequences of the row-reduced echelon form. I'll talk about this pivoting after I finish here. Okay, so some facts about the row echelon form. Now, let me point out, because you'll be using some software here. In Matlab, there's a command that will do this row reduction for you, and you'll be using that in your computing assignments. So for Matlab, the command would be RREF, and then you'd have the matrix as an argument. Okay, so if you've defined a matrix beforehand in Matlab, then you enter this command and it will output the row reduced form, reduced row echelon form. Row echelon form. And as you'll see as we go through this course, the reduced row echelon form of a matrix will have many uses for us. So it's a common operation. That's why they've built it into the matrix, the Matlab programming. Okay. Now here's an important idea. Unique row reduced echelon form. So the row echelon form is not unique. But the reduced echelon form will be unique. So that means if you're asked to find a reduced row echelon form of a matrix, we'll know exactly what the answer should look like, and you can compare amongst different people your answer, and they should all be the same. So you'd all be talking about the same reduced row echelon form. Okay, so it's unique. Okay, notice what they share, though, the reduced echelon form and the row reduced echelon form, is that they have the same leading ones. Okay, so the only difference between the two is you're eliminating the variables to get the reduced row echelon form. All right, so an important concept here is pivot, and that's used often in linear algebra when doing solving systems of equations or row reducing a matrix or doing operations on a matrix. We refer to these pivot positions and pivot columns. So the pivot column is the column that contains the leading one, and the pivot position is the location in the matrix that contains the leading one. Okay. Right. So now these are associated to the leading variables, the pivot columns, in the sense that, okay, so you have a pivot column, so that column contains the leading one. So the column, let me write it in our color. So the pivot column, because it contains the leading one, that corresponds to a leading variable. Pivot column corresponds to leading variable. Remember, in our augmented matrix, each column corresponds to a variable. The last column corresponds to the right-hand side. Okay, so corresponds to leading variables. And the columns without the leading variables are the free variables. So I should say, maybe because we're talking about the pivot columns that are not pivot columns, correspond to the free variables. Okay, so non-pivot columns, other columns, like the other ones, correspond to free variables. So counting the number of pivot columns is the same as counting the number of free variables, and the difference between the number of variables and the leading variables is the free variables. So the sum of leading variables plus the free variables gives you all the variables. A variable is either a leading variable or a free variable. Now pivoting, right, so pivoting is the operation that you do to eliminate those variables, okay, in the other equations. Okay, so we these are row operations, so it's a collection of row operations. To eliminate those in the other equations. Okay, so you have a pivoting position, so position in the augmented matrix, i.e. a variable, in a certain equation. Okay, so you do these row operations to eliminate that variable in the other equation. So here we need the non-zero entry in the augmented matrix in that position. So in other words, this variable you've identified to pivot on has a non-zero coefficient, so non-zero entry in augmented matrix. Okay, so that's the pivoting operation. And I should say here in the other equations, and create, in case there's not a 1 in the coefficient, a leading one. Okay, so all those together, when you identify a variable or an entry in the augmented matrix that's not zero, so there's a particular equation and you've picked out a particular variable in that equation that doesn't have a zero coefficient, you pivot on that variable or that entry in the augmented matrix. You perform, pivoting on that means you're performing the row operations that we've learned to create a leading one at that position, that location, and also eliminating all the variables in the other equations, okay, where that variable occurs. So in the augmented matrix, you're creating zeros everywhere else in the column where you've identified the pivot position. Okay, so although it's discussed here that the pivot columns and leading ones, we do pivot on the leading variables to create our reduced row echelon form. But let me just add here, you can pivot on any column, any entry, I meant, can pivot on any entry, any non-zero entry. And sometimes you do want to do that, even if it's not for the purpose of reduced row echelon form. You can pivot on any non-zero entry in the augmented matrix. Okay. Okay, so that's what pivoting is. It's a collection of row operations for a very specific purpose. But first you have to identify, let's just talk in terms of the augmented matrix. So first you identify an entry in the augmented matrix, or it doesn't have to be the augmented matrix, just the matrix. You identify an entry that's non-zero. Pivoting on that entry creates that a new matrix where that entry is a 1 and all the other entries in the column are 0. Okay, that's the final result of the pivoting. So the whole matrix will change, because when you're creating the zeros above and below that entry, you're affecting possibly the whole entire rows above you and below you. Okay, so it does change the matrix quite a bit. It can, but the final result will be that a 1 in that position and zeros everywhere else. Now I'll go up to here and show you what the code looks like in Matlab. I'll add parenthetically here, so Maple contains a pivoting operation, has a pivoting command. Okay, you can look it up. So in other words, you take a matrix, you define a matrix, and you want to use the pivot command. You enter the location of the element in that matrix you want to pivot on, and it will do these row operations and create the matrix as I've described. Matlab doesn't have that. So Matlab does the row reduced echelon form. So it will, if you put in to the command from Matlab, I should have, okay, I did write it here. So in Matlab, so it's RREF, M produces a row reduced echelon form of M. Okay, so Matlab will do that. It will do the pivoting inside there. It will do many pivoting operations, but it doesn't have a command that does a single one, whereas Maple does have that command. Maple also has the row reduced echelon form command too. So here's a little program just to give you some familiarity of Matlab, because you'll probably be using that to do your computing assignments. So this is a function created to do the pivoting. So it's called pivot. That's the name of the function. So the format here is the output will be this matrix R. All right, so I'll just say a few words about what's going on here. You'll become more familiar if you choose to use Matlab for your computing assignments. You'll quickly become familiar with the syntax and some of the commands that we'll be using. It's a really very powerful and commonly used scientific software. So it's worthwhile to get used to it as much as you can while you're a student here. You can access it for free as a student. Okay, so you can go to the IT computing and find out how to do that. All right, so first of all, so you input a matrix M, which you've defined previously, and then you want to do the pivoting on a certain entry. So there's your three things you input, M, R, and C. M is a matrix, R and C are two integers, locating the pivoting position. And here's the program begins. First of all, you didn't enter the size of the matrix, so there's a command in Matlab that will identify the size of the matrix. So there it is. So its output will be this array of two numbers. So now Matlab knows how big your matrix is. And then down here you'll see the pivoting operation. So the pivot location is RC. Okay. So you're going to go down and divide the entries in that column by this particular entry. Okay, so MRC now becomes equal to 1, which is what we want to create a leading one. And then we're going to subtract from all the other rows above and below this entry the required amount so that you create a 0. So that's this steps right here. Okay, so it will search through those entries above and below your pivoting position, and then it will add suitable multiples of the pivoting row to that row to create a 0. And then the output will be the final result. And here's an example of this done here. So I've written it out again. So my input was this matrix A. And you see how the command worked. You call the function. If you didn't put a B equals, it would just output this matrix on your screen. So if you write B equals that, then you've created this matrix B, which is the row reduced, or not the row reduced, but the result from pivoting. So the pivot entry, if you notice, is 1, 1 here, 1, 1 there. Okay, so I've highlighted it here. There's the pivot entry, 1, 1. So you can see that it works. It creates a 0 where the 2 is, and then the second row is being modified appropriately. So the row operation, you can see what it was. It was subtracting 2 times the first row from the second. Okay, and you can see that that works, gives you that answer. And just for us practice, if we pivot on the entry 2, 2, so let me do that. That's this one right here. So this is what I'm doing now. Pivoting on 2, 2 is not something you would do if your goal is to find the reduced row echelon form. You can see you would pivot on the 1 if you're trying to produce the row echelon form. Then you would pivot here, okay, on 1, and then you'd be done. But like I said, it does occur from time to time that you want to do a pivot on a particular entry that's maybe not the one you would select when doing row reduced echelon form. So let's just do that. So let's pivot on the entry 3. So I'm going to write down what, first of all, I changed that 3 into a 1. So I'm going to divide row 3 by 1/3. So I'd get 2/3, 1 4/3. All right. And then I use that 1 to eliminate the variable above. So for this new second row, I'm going to subtract twice it from the first row. Okay, so I can eliminate the 2 in the second entry in the first row. So when I do that, I'll get 1 minus 4/3, which will give me, 1 minus, 4/3. So I'll get minus 1/3. Okay, and then my 0, and then I'll get 3 minus 8/3. Okay, 3 minus 8/3, so 1/3. 3 minus 8/3. Okay, so that would be the result of pivoting on that entry there instead of the 1, 1 entry. Okay, so that would be the output there. So back to this page here. So solving systems of linear equations. So this is what we've been doing in the previous lecture, and we just extended it a bit here. So you start with a system of equations. Okay, so system of equations. And then we put it into an augmented matrix. Remember, that was our notational method to keep track of these operations. Matrix. And then once we had that, we applied the row operations. Okay, and we will keep applying row operations till we get to the row reduced echelon form. And then we identify, once it's in that position, the leading variables, which are occurring in the pivot columns. Okay, and these are the columns with the leading ones. And we identify the free variables, if there are any. They don't have to be any. So these are all the other variables, the variables associated to the columns that don't have the leading one. Okay, and then we can write out the solution set. And it will have infinitely many solutions if there is at least one free variable. There may be no solutions, right? So remember, we can recognize in the reduced form even whether a system's inconsistent or not. So that's also very helpful for us. All right, so that's where we are. So now we introduce some more definitions. So the rank is an important parameter for a matrix. So the rank of a matrix is the number of leading ones in its row echelon form. Okay. So right away I know that it's no larger than, so rank is no larger than the number of columns. Okay, because you can't have more leading ones than columns, so no larger than number of columns in the matrix to begin with, but the rank can be anything less than that. Okay, so here's what we'll be using to denote this integer, rank A. So some work has to be done to determine the rank of a matrix. If it's not in reduced or row echelon form, then it's not obvious what its rank is. Okay, so I look at this matrix here, for instance, and I can identify, so this is a reduced form, and I can see that my leading ones are here. Okay, so I see 3 leading ones, so the rank will be, the rank of this matrix is 3. Okay. Now rank is related to this notion of consistency that we talked about for a system of equations. Remember, consistency means that consistent system of equations means there's at least one solution versus inconsistent, which means there's no solution at all. So given so a system is consistent if and only if the rank of the matrix, coefficient matrix, now notice this, is equal to the rank of the augmented matrix. So we're talking about 2 different matrices. So one is the coefficient and one is the augmented. Okay, so remember the difference between the two. The coefficient matrix is what you obtain by removing the last column of the augmented matrix. Okay, so you just remove the right-hand side from the system, and then you just look at the coefficients in front of all the variables. So the coefficient matrix is obtained by removing last column. So they look very similar, different sizes, but they share the same coefficient part of augmented matrix. Okay. So we can write down an example here. Okay, so there's a, for example, let's just take this one up here. So 1, 2, 0, 0, 1, 0, 0, 0, 1. Okay, so suppose I have this matrix here, And suppose this is the okay, so suppose this is the an augmented matrix. Okay. Now the leading ones are these variables: 1, 2, 3. Okay, matrix. And then I see the rank is 3. But the coefficient matrix here is this one, right here. Okay, this is the coefficient matrix. Okay, and the leading ones. So the leading ones in the coefficient part will be there, but notice in the augmented matrix, one of the leading ones is in the right-hand side. And so this is, we identify this row here where there's a leading one in that last column as indicating it's inconsistent. Okay, so this row identifies that system as inconsistent. So the rank of the coefficient matrix here is smaller, right? Rank is 2, I mean. Okay, so in general, the rank of the coefficient matrix will be no larger than the rank of the augmented matrix, just because the augmented matrix is adding another column to the coefficient matrix, which means you could create a leading one, but you don't have to, right? So it's never going to be the rank of the coefficient matrix will never be larger than the rank of the augmented matrix. But when it's strictly less than, like it is here, that indicates that there is a leading one in the last column, and that of the augmented matrix, and therefore it's inconsistent. So that's the justification of this sentence here. The ranks are the same, then it's consistent. If the ranks are different, it's inconsistent. And different because of the sizes, the relation between the sizes. If they're different, it means the coefficient matrix has less rank than the augmented matrix. Okay. Now, because the rank is the number of leading ones, then it's also telling us the number of free variables in the equation. Okay. So we have, where was I here? Good. Yeah. So the number of columns, remember the number of columns right, the number of parameters. So the number of columns in the coefficient matrix is the number of variables. And I should emphasize here, there's a key word here we can't miss. It's a consistent system. All right. So for a consistent system, considering the coefficient matrix, which is sufficient for our purposes because that extra column that appears in the augmented matrix is not going to affect the rank, okay, because it's consistent. So let's just talk about the coefficient matrix. So the number of columns in the coefficient matrix is the number of variables. And so the number of free variables equals number of variables minus number of leading variables. And the number of leading variables is the rank of that coefficient matrix. Okay, and this is the number of columns. Okay. So number of columns minus the rank is the number of free variables. So number of free variables equals number of variables minus the rank. Okay. So that's something we can use to determine questions about consistency and also questions about whether there's infinitely many solutions or not. Remember, for consistent systems, the existence of a free variable, at least one, implies that there's infinitely many solutions. So if there happens to be a unique solution to your system, that means there's no free variables. Okay, no free variables. So the rank has to be a certain size for that to make the free variable 0. Every variable is a leading variable. All right, so an important class of linear systems is the homogeneous linear systems. So I've mentioned homogeneous systems before. That is the right-hand sides, which we were calling B's, are all 0. Okay, so the right-hand side is all 0, and therefore the that column in the augmented matrix is all zeros. Okay, so that final column will be all zeros. Now, homogeneous systems are consistent. Let me write that in red. So homogeneous system, and that's the reason is just given below. So homogeneous systems are consistent. So we don't have to do any row reduction to answer that, and you'll see why. Homogeneous systems are consistent. Okay. Non-homogeneous systems, typically we can't tell whether they're consistent or not until we perform some row operations. Okay, but for homogeneous systems, they're consistent. And the reason is the following, right here, that the trivial solution, so this trivial solution is xi equals 0 for all I. So all the variables are 0. Set them to be 0, then you get a solution to that system. So remember, you know, a homogeneous system looks like this. So I'll just write out one equation, a1 times x1 dot dot dot. So this is what one of the equations would look like. Okay, so you have all the variables appearing. There's the coefficients. Some of these a's can be 0, but the key point is that the right-hand side is 0. So you see why when all the x's are 0, you get a solution because the left-hand side is 0. That's called the trivial solution. So that solution is always there for a homogeneous system. Therefore, it's consistent. Okay, so that's given. So that means what's interesting for homogeneous systems is when there's non-trivial solutions. Okay, so i.e. at least one xi is not 0. Okay, and that would mean that there's at least two variables that are not 0. So you need some cancellation going on to make the left-hand side 0. Okay, so in other words, they're not all 0. All right. Now, a few facts about solution sets of homogeneous systems are pretty easy to prove right now. So here's one solution, non-trivial solution. So, well, there's one solution of it. If it's the trivial solution, then the s's are all 0. Okay, but let's assume that it's possibly not the trivial solution. So there's a set of n numbers, which when I plug it into my equation, gives me 0. So what this means is, I'll do it over here. It means that a1 times s1 plus dot 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 plus an times sn is 0. Okay, so that's what it means for in all equations when I plug it in. Okay, I always get 0. Okay, I've just written down one equation in the system, but if you plug in s1, etc. for the x's in every equation, they'll be equal to 0. The claim here is that if I have one solution like this, okay, so now I'm going to assume that it's not the trivial solution. Then when I multiply each one of them by the same k, that's what it is here. Okay, so now I get another non-trivial solution that's different. It's also a solution, and I'll explain. It's easy to see why that's true. So I'll just once again look at one equation here. So in other words, what happens when I plug in not s1 but k times s1, etc. So I'll get a1 k times s1 plus dot 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 plus a n k times sn. Okay, so that's what it's claiming, that this new set of n numbers, ks1, etc., is a solution. Is it a solution? Let's check. So let's rewrite this then. So I plugged it into one of the equations. I can factor out this k from all of them. So I'll get AS1, A1S1, dot, dot, ANSN. Okay, fine. But now I use the fact that the S1, S2 to Sn is a solution. So that's 0. Okay, so it's k times 0, and I do get a 0. Okay, so if I've identified one non-trivial solution, and notice this argument only works for the non-trivial solution, because the trivial solution, if you multiply it by k, you don't get a new solution. It's still the trivial solution. But for a non-trivial solution, if you multiply by a k that's not 1, say, I should have said that. If the k is not 1, then you've created a different solution, and it is a solution as we've identified. For any scalar k, true. So k could be 1, but that's not interesting. K could be 0, but that's not interesting either. It's for those other k's. These are the new solutions we'll get. All right. So for homogeneous systems, once again, there's either just one solution or infinitely many. Okay, one or infinitely many. So the option that's missing here for a general statement. So there's a similar statement for a system of equations, as we've seen by examples, and we're kind of working our way. I mean, if you think about it, you can prove this statement here, that the solution set of a system of equations has either 0 solutions, 1 solution, or infinitely many. So what's missing here is it's never inconsistent, never no solutions. Okay, so that's the only thing that's missing for homogeneous systems, because they're always consistent. So maybe I'll make a note here. Note, and you should think about this. I mean, I didn't sit down and explain this in detail, but all the information you need, I mean, the reduced row echelon form of non-augmented matrix will allow you to do this. So note that every system of equations has either no solutions, exactly one solution, or infinitely many solutions. I can say a bit more about this. So not true. So a general statement like that is not true for nonlinear systems, nonlinear equations. So for example, quadratic equations, say a homogeneous quadratic equation can have 0, 1, or 2 solutions, right? 2 roots. Okay, so exactly two solutions will never occur for linear systems or linear equations. It's only 0, 1, or infinitely many. And you can see that for yourself by considering the row-reduced echelon forms. Okay, so I think that's about all we'll talk about in terms of reduced row echelon form. It's going to be a main tool for us for the whole course. Okay, it's going to be in the background all the time. So if you're feeling a little anxious about doing all these row operations and reducing matrices, you're going to get plenty and plenty of practice, so you'll become pretty proficient at it soon enough. So let's talk about, let's connect some of the abstract ideas we've talked about in previous chapter about vectors, in particular the solution space. So I've been calling it a solution set, right? Solution set so far. So now when we introduce this term space, we're talking about subspaces. So in the case for a homogeneous system, and we'll see why it's not true for non-homogeneous system, the solution set, so there's the word set again. Remember, solution set is a set of vectors. Remember those n tuples of numbers, set of vectors in Rn. where you have n variables, right? That's what a solution set is. It's a subset of vectors in Rn. And in that lecture about subspaces, we asked when is a subset a subspace, and there's closure properties. So we're using, now we're going to talk about sets of vectors that are solution sets. And in particular, we're focusing on the homogeneous system. So its solution set is a subspace, okay? So that's why we can use the term solution space rather than solution set. Okay, that's the reason we use the word space. Well, we should do the proof because it's going to refresh our memory about subspaces. So remember, the proof is to show closure. Okay. So that's the difference between a subset of vectors and a subspace of vectors. The subspace of vectors is closed under the two algebraic operations we define on vectors, that of vector addition and scalar multiplication. Okay. As an aside, remember I said that you know, when you're tasked to prove whether a subset of vectors is a subspace or not, you could launch into the proof of closure or attempt to prove closure. Okay. If you can't prove closure, then you have to prove that it's not closed and therefore not a subspace. So one easy way to show that a subset is not a subspace is to show that it does not contain the zero vector. Remember that? So if you can show that it does not contain the zero vector, which often is easy to do, then you've finished the proof because you've established it's not a subspace. However, the caveat is that if it does contain the zero vector, then you have to launch into a proof of closure or a disproof of closure, because a subset containing the zero vector in itself is not enough for it to be a subspace. So here I'm just saying, you know, you might start off these problems that way, you know, a kind of easy way out. If it turns out not to be a subspace, maybe the reason it's not a subspace is because you can see that there's no zero vector in that set. But here, if we tried that, note that the zero vector is in there, is in solution set. Okay. And that was described above. Okay, so I did that up here, right here. Okay, just emphasizing one of the equations out of the many. Okay, so 0 is in the solution set of a homogeneous system. Okay, so I can't use that strategy to prove that it is not a subspace. In this case, it turns out to be a subspace, so we're going to show closure. So let's do, so above we did that one. I'm going to just write it here. So it's closed under scalar multiplication, and that's the one I did above. I'll indicate what it is. Okay, and that was up here. This one I did right here. So that's one reason I decided to do it here. So there it is. So I took a solution, S1 to Sn, that's a point in the solution set. I multiplied it by the scalar k, and I demonstrated that it's in the solution set. And the only way to demonstrate it's in the solution set is to show that when you substitute those values into the equations, every equation, here I'm just writing out just one example of an equation in the system, I'll get 0. Okay, so I've shown that. So it's closed under scalar multiplication. Let's do closure under vector addition. So closed under vector addition. Let's prove that. Okay, addition. All right. So so let's give some names to these sets. So solution set is, let's just call it S. So let. So now I want to prove this set S is closed under vector addition. So I'll take two vectors, v1 and v2, from the set S. Okay. So what that means is that these the components of these two vectors, when you substitute them into the equations for the variables, all the equations equal 0. Okay, so it's a solution, each one of them. So now I want to look, I ask this question, is v1, the vector sum, is it in S? Okay, so that's what we need to study. So let's check. So IE is, so I should write down first some of my variable components. So let's let V1 equal, let's call it S's. So S1, Sn, so that's its components. And let's say V2, its components, let's call them T's. Okay, so there's my components of my two vectors. So is, when I ask for the sum, I mean the vector sum, so that's the first component of my vector sum, and this is my last component of the vector sum in S. Okay, is it in S? I should just mention that. So this means in set S. So that's a common terminology for us in math, this little symbol. So is this in S? Well, remember in these problems about proving a subset is a subspace, at this stage you have to go to the description of that subset. However it was described is what you need to use to identify whether a given vector is in the set or not. So this subset was defined as the solution set of a system of equations. So I have to test whether a vector is a solution to the system of equations to determine whether it's in the set or not. Okay, so I'm going to check that now. Check whether this vector here, I've just written down S1 plus T1, etc., is a solution to the system. So what does it look like? So for one equation, I would have something like this. Sorry, it's going to be my coefficients, right? It's going to look like this. So one equation, so I'll have A, and then for the x1 variable, I'll have S1 plus T1, A1, let's call it, and then I'll have the coefficient for my x2 variable in this equation will be S2 plus T2, etc. And then I get to the final coefficient in front of xn, and its value is now Sn plus Tn. Okay, so I've substituted into one equation, so substitute V1 plus V2 into one equation. Okay, it could be any one of the equations. I only need to look at this one. All right, so that's what it looks like. And then I'm going to rewrite that as, okay, so I'm going to write that as, I'm going to group it together. So I'm going to distribute the A's across these S's and T's, and I'm going to group together the S's and the T's. So I'll get A1, S1 plus dot 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 AN SN, okay? And then, I'm putting these brackets in artificially just to group together the two distinct terms. Then I'll get A1 T1 plus dot 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 ANTN. All right, so I'm just doing algebra. Okay, so remember the first step was, okay, this is how I determine whether a vector is in that set S. I have to substitute its components into the variable positions in each equation. Here I'm just writing down one equation. And then my goal is to determine whether this now sum of numbers is equal to 0 or not. So I'm doing some algebra. And I have to use, at some point, I'll have to use that the V1 and V2 are in the set too. Okay, so that's another kind of strategy for you guys when you're doing proofs like this is make sure, like I mentioned before, you're using the definition of the set of vectors, but also make sure you're going to use the fact that you've selected two vectors already in that set. So they have certain properties. You have to use those properties. I'm going to use them now. So I know that this vector S1 to Sn is in the set, so it's a solution to this equation and to all equations. And I also know that this vector T1 to Tn is in the set, and therefore it's a solution to all equations, so that's equal to 0. Right? So I've used that property now, and then I determine that I get 0 plus 0, and therefore it's 0. Okay, so my vector V1, V2 is in the solution set. Okay, so V1 plus V2 is in S, and that's the end of the proof. Okay, so proof following our steps as described in that previous lecture. So there we've started to see some connections between what looks like a very concrete types of calculation solving systems of equations and this more very abstract ideas about linear combinations of vectors and subspaces and closures of sets of vectors coming into play into this concrete situation. And that's the power of linear algebra, was this realization that there's this abstract structure going on in the background when you're doing these very practical calculations, and that kind of led linear algebra to be quite an abstract subject. But as you'll see, and as you become more proficient and more familiar with the use of linear algebra, that it's these abstract ideas that are really making linear algebra a very powerful tool in applications. Okay, so that's enough for today's lecture. I will stop the lecture here and see you next